guys, let's start. So this is a mathematical reinforcement. We have a lot of load in the following, not as much as it was in the beginning of the course. The beginning of the course is the hardest part, okay? If you are here, the hard part is behind you, okay?
Thank you so much.
But
And clearly not.
if you survive, this was the survival function. Okay, so what we're going to talk about now is some mathematical basis for also things that was talking about regarding the coding, which will be the first part of the next recitation, and also a bit about information theory, which is probably the newest thing for all of you. So we will just really go quickly on the basis, and then we'll focus on the information theory. So just to be sure, I want to talk first about finding minima and maxima. This is something which all of you should be familiar with, because it's using the derivative to find minima and maxima. So maybe just a short reminder about the derivative. This is the definition of derivative from Britannica. Derivative in mathematics is the rate of change of a function with respect to a variable. Okay, so therefore, if we have this function over here on purple, and we want to know how much does this function changes from point x0 to point x0 plus h, which is point A and B. So we can take the slope, the linear slope between the two, and this is the change. Now, if we take these two dots and make them much more closer, infinitesimally closer, as if these are the most adjacent 2 points on the function, then we have this derivative, which is also the how do you call it? That it goes only through 1 point. Tangent line of the derivative, right? And then we can use the derivative. Yeah, I was also not quite sure about that. And then we can use the derivative, as you can see here in the plot from Wikipedia, that whenever the derivative is positive, this means that we are going upwards in the function, and whenever it is equal to 0, this might mean that we are at a minima or a maxima at one of the optimizations, right? And when it's red, you can see that it's going downward, the function. This means that the derivative is negative, okay? Mm-hmm. And over here, we can also see, I don't know the name in English for this kind of point, that the derivative is 0, but this is not a minima or maxima. Platon is it called? In Hebrew, it is called nekudat ukaf, or sem. If you want to know if this point is a minima or maxima, you need to have a second derivative. And then if the second derivative at this point equals 0, that means that it's neither minima nor maxima. If it's positive, this means that we are at a minima. And if it is negative, it means that we are at a maximum. Okay? All of these things are things that you should be familiar with, because in the beginning of the recitation, we are going to find minima and maxima analytically by calculating the derivatives of different types of functions, okay? And of course, when you are in the real world and you want to find the minima or maxima, so you don't use the derivative, you use other algorithms from computational science, right? from computer science, such as gradient descent, and this kind of things that Izar was talking about. And this is not, this is one of the subjects that we won't teach during the course beyond just some enrichment, but this is a very, very important thing to understand about how you calculate the optimization. Okay, so just a short reminder about the rules of the derivatives. If your function is constant might be 1, 2, e, pi, -1, 0, any number. If it is constant, then this is a flat line, and its derivative is 0. Okay, all of the derivative. If you have a constant multiplied by a function, then the derivative is the same constant multiplied by the derivative of this constant. The constant multiplied by the derivative of the function. In the power rule, we commonly use it. So if we have x and this is powered by n, then the derivative is the power multiplied by x powered by n minus 1. And then we know that the derivative of two sum or difference between two functions, this equals to the sum or difference between the two functions, and we have the product, right? Do you remember the product? If it's multiplication between the two functions, so the derivative is the derivative of the first one multiplied by the regular function plus the regular multiplied by the derivative. And we have also the quotient rule, which is the division between two functions, and the chain rule that if we have a function of another function, then the derivative is the derivative of the outward function multiplied by the inner derivative. Okay, so now let's have a short example. So let's calculate the derivatives of such a function. Okay, so if we have y equals x by the fourth plus e minus x squared multiplied by sine x, then the derivatives are, so first of all, we make a derivative of this first function, which is 4x. Great, 4x by the third. And now we need to make a derivative of this function, which means that we make a derivative of this one multiplied by this one. And we add the second one, the first function, without its derivation, multiplied by the derivative of sine x, which is cos of x. Right. Okay, so now all that we have to figure out is the derivative of e minus x squared. And here, this is the chain rule, right? Chain rule? No, it's the how is it called? Chain? Yes, it is the chain. So now we need to first have a derivative of e by what is the derivative of e by t? Et. And then we need to multiply it by the derivative of t. So over here, when t is minus x squared, it's e by minus x squared multiplied by minus 2x. Okay? And when we put this here, we can find when does the derivative equal 0, and this will lead to when what are the possible minima and maxima of these functions. Okay? Great. So you know how to go on from here. Yeah, I don't know. I think that most of you are okay with it, right? So no need to do the second one. Okay. So if you need to find an absolute minima and maxima, just a bit from Khan Academy, you can watch these videos or another short video that I added here. Right. Okay, so any questions so far? Okay. So the second subject is the subject that we were already talking about logarithmic scales, but now we are going to use it in information theory. So I just want to remind you some of the rules, and then I want to give an example how we use them, because this is something that we didn't do in the previous subjects. Okay, so I'm just reminded that what does log mean? That if we have a number powered by another number, and this equals some number n. So b, for example, is 2, a is 3, and n is a. Then the logarithm is like asking the question, what is the power of the base number that we need to get into this result? Okay? So we can see it here. So what is the power of number 2 to get to 8? We need to multiply it by 3 times. Therefore, the log is 3. Okay? Great. So there is a relation between logarithm and exponent. So this is the direct connection that we were talking about here. Again, we have the base, we have the number, and this is the log. And we have the common log, which is for base of 10, and the natural log, which is for base of e. And we are going to use a lot the log of base 2, okay? Here in information theory, we have a good reason to do it. We'll talk about it more in details tomorrow. And okay, so this is the function, and here we are going to talk about the rules and use them. So if you want to understand the relation between exponent and the logarithm, so we have this symmetric line of y equals x. And then we have a symmetry between the exponential and its log, okay? Now, some of the things that we need to remember about log. So any number that we have here inside the log must be greater than 0, okay? Okay, and now the main rules that we use is that logs allow us to transform a function from multiplicative function into a sum of functions. Okay, and this is very helpful when we need to use it in information theory. Okay, so in information theory, sometimes we have a lot of multiplications between function m and n and another function x and so on, and then we put all of them inside the log, and then we can move it in, from multiplication into sum. And similarly, we can do it about division, okay? And when we have a power inside the log, we can take the power out and make from it a multiplication. So some say that the log takes the order of complexity always down, right? Because if you have here a power, then this turns out into a multiplication. If you have your multiplication, you can take into the log, and then you have sum, right? So some of the computations that we do in computer science are using this relation to make them easier. Okay, and I don't know if we even need to talk about that. Of course, here log of b of 1 equals 0, okay? And if you have how do you call it, a fraction, right? A number that is smaller than 1 but bigger than 0, then the result will be negative, okay? So please note that there could be a possibility that log of 2 of quarter, this equals -2, but log 2 of -2 does not exist. Okay, please note the differences. The output can be negative, but inside the log function, you could not have something which is negative. Okay? Questions so far? Okay.
I was just wondering why it's impossible that b equals 0, because we know that 0 to the power of anything equals 0.
Okay, so let's figure what does that mean. So if you have, for example, log of 2 of 0, this means that you have,
I'm sorry, the base. Like, I mean, why is why the base cannot be 0?
oh, I meant that inside the log,
Mhm.
the number could not be 0.
Okay.
So let's think why, if you have 2, what power should it have to be equal to 0?
Yeah, it's impossible.
It's impossible. So for this reason, here it's always greater than 0. It's always positive. Okay? But the base of 0 means that here any number is either 1 or 0. That's it, right? Because 0 powered by 0 is 1, and these are the only possibilities. So either 0 or 1. I don't think that we use log of base 0.
Yeah, it makes no sense. Because
Yeah.
I was just surprised that the calculator refuses it. I thought it would be like equal 0.
Because the calculator uses this Taylor series. You know what is the Taylor expansion? So, like the way that the calculator works, it doesn't really compute the log. It's not that it has a lot of possibilities and then it tells you, oh, if it's 0, then this should be this and this. No, he has a kind of approximation, and then it gives you this approximation. But this will be discussed on a different course. Okay, so let's see, for example, how we can use a log to find the minima and maxima of a function, which is one of the ways that we are going to use the logs. So if we have this function, and then we want to find its minima and maxima, how do we do it? Right, so we can either use the product law, right? Which means that I can write f of x is like x squared plus 1 times sine of x e times e by x squared plus 1 times 1 over x plus 3, right? And then the product law says that the first way to calculate it is by, first we need this derivative, which is 2x, multiplied by sine x e by x squared plus 1, L over 1 by x plus 3, and this is plus the original function with this derivative, right? You see where is it going? It is off. Okay, and then we need to have a derivative of such this one, and then when we take it here, we need to use it again and again. And this is really, really, really long, and we don't know if things will cancel out and so on. So another possibility is to take this function and just put it, and just put it inside a log. So a log of this function times sine of x times e by x squared plus 1 times 1 over x plus 3. Okay? And the thing about the log is that it conserves the it conserves the function upwards and downwards, okay? So you can take any function, put it inside the log, and then just have the derivative of the log, which is easier, okay? So let's see over here. So instead of multiplication of this different function, this equals to log of x squared plus 1 plus log of sine x plus log of e by x squared plus 1 plus log of 1 over x plus 3. Okay?
Then the actual value of the derivative is not going to be different because we use log?
So the idea is that the same x's that are that for them the derivative of the log equals 0 are the same x's as the original function. Okay, because it conserves the same upwards and downwards across the function. Yes.
And this is just for multiplication to sum, right?
Exactly. And then when we need to have a derivative of this one, it is much easier, right? Because what is the derivative of log x squared plus 1? The derivative of, let's have ln instead of log, it will be easier. Okay, just replace all of them to ln because it is much easier and it conserves the same basic idea. Okay, so the derivative of ln x squared by 1 is 1 over x squared plus 1 times 2x. Okay? And the derivative of this one is 1 over sine of x multiplied by the inner derivative of sine x, which is cosine x, okay? And so on. Okay? That clear? Great.
Where does it say cosine of s? No,
So this is the inner derivative of ln.
and then in the end, it says cosine, the last part, yes.
Here.
Yeah, and then plus,
Plus, and then you have this one, right? And you need to write it here. But the basic idea is the same. It's the fact that you took multiplication of functions, you put it inside a log or a ln or whatsoever can be easier for you. And then you make a derivative of it and you find the optimal points. Okay? Great. Yes.
I was trying to finish the.
Okay, so
the
let's.
line, but I'm not able like to do that.
Great, so let's try. So every derivative of ln is 1 over what is written inside this ln. So
Times
it's
the-
1 over e by x squared plus 1.
Don't just cancel the E and LAN and stay with just.
I can, but I just want to
Okay.
show it, yeah. They are consolidations anyway. So now I need to make a derivative of this, right? So what is the derivative? So again, we have another chain rule. So it's the derivative of e by t multiplied by t tag. So it's multiplied by e by x squared plus 1 and by the derivative of x squared plus 1, which is 2x. And these two are canceling out, as you just offered. And then you have this x, 2x. Now what Ori said that anyhow, ln of e by something is just this something. So you could just write here instead x squared plus 1. And this is the same. Okay? Okay.
Yeah, this is why did you choose for not long? Just because.
Just so that we have this nice derivative of 1 over.
We can do both.
Yeah, because for log, you need to also multiply by a of something, by the base, by. So I just left it out. Yes.
And once you change one to nine, all of them have to be changed.
Here, yes, the idea is that you did lan and all of the functions were inside, and then you make it from multiplication into sum. This is the main step that I want you to remember from this reinforcement, okay?
Can we do the last one?
Yes, right, so let's have the lan of 1 over x plus 3. So this is 1 over 1 x plus 3, and this equals to x plus 3, right? And this, oh, by the way, multiplied by minus 1. Minus 1, or I need an inner derivative of this. So the inner derivative of this is, sorry.
Would it be minus 1x?
No, it's not minus 1, it's 1 over x plus 3 squared.
It's not.
I think it's -1.
It's -1.
Minus 1, right. And an easier way is just to write this as x plus 3 by -1, taking out the minus here, and then just making a derivative of this, right? Yes, so an easier way, instead of doing like 1 over what is inside the lan, and then by the inner, is just saying, okay, here it's x plus 3 powered by -1, right? So I can take the minus outside, and then I have lan of x plus 3. So this is the same as the one that is written here, but much easier and with less complications. Right, so we had here all of the rules of logs. So from multiplication, we moved into sum. And then here we use the fact that lan of e by something is just equals to this something. And here lan of 1 over x plus 3. So we can write it as x plus 3 powered by -1, take the -1 out, and have a lan of x plus 3. Okay? Excuse me? Minus lan, because the minus went out. Okay? Possible. Right? Not impossible.
Why the minus?
Here? So it's like plus multiplied by -1, right? You take the power outside, like we saw here. So you have the power and you take it out. Great, okay. So now we are ready for information theory. And I won't teach all of the information theory ideas, but only the very basic one of entropy. Okay, so again, Izam will teach everything much more organized tomorrow. I just want to very shortly explain the main idea of entropy, so it will be easier for all of you to understand it tomorrow. So first of all, just a short introduction. Information theory was developed during the Second World War. That, like many of the subjects that we use today in computational sciences. And the basic idea is that it was the question, what is the shortest way to take information from one place to another? How can you encode a message by bits, for example, or by any other encoding possibly? Okay, just think about ciphers. What is the most sufficient way to write a cipher? Okay, and then The information theory was developed to calculate what is the shortest way and what is the easiest way to transfer this information. Okay, so information theory is commonly used for nowadays for computers in networks that they need to communicate with each other, and then you need to ask yourself how much information might be lost, right? Because when do you know how computer sends a message on the World Wide Web? Okay, so computers talk with each other by 0 and 1. And then, for example, any letter can be represented by 8 digits, which is a byte, right? Of 0 and 1. For example, A is 0, 0, 0, 0, 0, 1 in the end. B is 0, 0, 0, 0, 0, 0, 1, 0, for example. C is 0, 0, 0, 0, 1, 1, okay? So you have all the possible letters represented by bytes. And then when you send your byte on the computer, so the computer is just close, for example, if you have this optical wire, so there is light, dark, 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 light, dark, and this is letter Z or something like that, okay? So when the computer transmits its information into the network, okay? So some information might be lost. For example, in the middle of the way, the digit, one of the dark digits, the 0, was lost. And then you need to ask yourself, how can you make it more sufficient, for example, by using different routes to combine data and things like that, so that information won't be lost, but you won't need too much information because you want to keep it fast, okay? So information theory is the way to calculate these kind of things. And now you can really easily understand why in neuroscience, the idea of information is very useful, right? Because when we use information, we want to speak about how different regions of brain are communicating with each other.
Come on, Arma, you're not so sensitive. Where Brandon's going. Come on.
1 minute, okay. So if we want to calculate how different regions of the brain are communicating with each other, then we want to think how they are, how much of the information might be lost, okay, and is it sufficient, and so on. So this is the basic idea. And it's not heavily used in neuroscience. I mean, like sometimes you can see that the entropy is this and this, and the mutual information is this and this, and these are just not very hard computations, okay? It's not like the autocorrelation and cross-correlation that you really need to use the computer to solve them, because otherwise it's really long, right? Just all of these kernels that you need to oppose them and so on. So here you don't really need the computer, but you calculate them, for example, by saying, so you can see that the mutual information between these spikes and these spikes is the lowest, okay? And we need to understand what does that mean. And also in project 3, your third question is analytically solved for this reason, because in information theory, we don't commonly use it computationally, okay? Okay, so let's see what entropy is. So when we say entropy of a system, for example, entropy of a brain, entropy of a computer, entropy of a neuron, is the level of uncertainty about the state of that system, okay? So this is a very vague definition. It comes from physics. When they talk about the differences, you should know even better than me when calculating entropy in thermodynamics view. Christian, right?
I mean, yes, but do I remember? No.
So this comes from physics and chemistry, that you need to calculate the level of entropy of a gas in relation to the level of entropy of a liquid. But it is much more easier to understand entropy by the expected number of bits required to fully describe the state of the system. Or another way to understand, okay, so therefore, if I want the system to be at the mode of A, this is the minimum number of bits, okay, that are required to fully describe A and B and C and all of the possibilities of the system. Okay, another nice way to understand it, and it's here in the recommended links. So this is a great textbook that Benji sent me about information theory. So a nice way that they describe it is that, you know, this game that like in Inglourious Basterds, that they have this card over here. I hope that all of you have seen this movie, and if not, you need to do it by Wednesday, okay? A great movie. A bit violent, but you can make it. After the 7th of October, there are no violent movies anymore in the world. Right, so when, sorry for the black humor. So when you have a card here in the movie, so each one writes a name of a character, and then they put the name of the character here, and then each one needs to ask question about this character, and if you decipher who is the character by less than 20 questions, then you don't have to drink. It's a drinking game, so you don't have to drink a chaser. Okay, and if you didn't decipher, then you have to drink. Okay, so it's a very nice game, and you probably know it. It's called also 20 questions, and then there is of course the question, who decided about 20? Okay, so why do we need only 20 questions to decipher any possible character in the world, right? And the number 20 comes from information theory, because this is the minimum number to describe any possible character in the world. I think it's even less. There is like this computer, you know, that there is in the internet that you can play this 20 question game. Excuse me?
When I was young,
Yes, yes.
I was playing this Akinator.
I think, yes, something like that.
And James
Yeah.
asked the question. And
So how can he do that? So he uses like a set of questions that he goes in between all these possible questions, and then it's 20 questions max, right? So you need 20 questions to describe any possible character in the world. Okay, so entropy is the way that we can calculate it. And for any kind of system, we have a different entropy. So what is the direct calculation of entropy? It is given by age of system X, okay? Which is the random variable. This is the RV, right? So the entropy of system X is minus the sum of all possible states of this system, right? All the probabilities multiplied by log of base 2 of these probabilities. For example, if we have a coin, yes.
For each.
Please ask it again. Okay. Yes.
No, I think I was thinking that like for a character, so it's like a possibility, and then you have a no and a yes. So maybe that's why.
Yes, exactly.
Maybe that's.
No, you're right. It's exactly like this, because anytime we reduce it to 0 and 1. Yes, you are right.
What is on the other side of the sigma?
Yes, the minus, because
No,
log.
what is above? I mean, it goes from X. I mean, how many summations are we doing?
So as the number of possible states of the system, for example, if we look at the ABC, so we have 27 letters, right?
It depends on which language.
So, for example, in English, it's 27. I don't know for
X.
But I don't fully remember, sorry. 26, okay, great. And then you have the lower letter, the higher,
Okay,
I mean like the capital
Yeah.
letter, and all the numbers.
okay.
So you have 26 double, this is 52, and all of the numbers, it's another 10 possible digits. So it's 62, and this should be transferred into 8 bits.
Why double? Sorry, I don't know.
So if you have A, B, C, you have the lowercase and the uppercase. So it's double, and then you have all the numbers. So as far as I remember, when you calculate the entropy, I don't really fully remember. But as far as I remember, when you calculate the entropy of all possible letters in English, it sums up to entropy of 8. 8 bits is the minimum number of bits that you need to describe any possible letter by computer, including numbers, yes.
Wait, but, you just said that, there's like 62, I think you mentioned.
Yeah,
So like, the P of each event is like 1 to
1
62?
over 62. Okay.
Okay,
And then you have log 2 of 1 over 62. And if I remember right, it sums up to
and
8.
what is sum? I mean, like, is it like a loop that goes to like, so the next one will be, 2 over 62 until we reach.
I don't know, for each probable letter, it's 1 over 62.
So what is?
So
sum?
only if you have,
What does the sum mean? I mean, what do we sum?
so if you have different probabilities, so let's say that you have a die, and this is not a fair die. So you have a double possibility of getting 4
Okay,
and lower for others, then
Okay.
the entropy of the system will be different than a fair die. And it's a very, very good question that we will discuss about uniform distribution in relation to other types, but I really want to keep it to the discussion in class.
the probability is not of an event out of all the system, it's just for an event in the system, I mean,
Yeah,
okay.
yeah. So you sum up all possible states, all possible events.
So
Yes.
the result of the entropy is not 8, is like,
It is 8.
is 8?
It is 8. It's the number of bytes that you need to encode any possible state. So
But wait, I can look at the same, at the same, question that you mentioned, for like,
it's,
look at it at 52 different, letters, and,
yes.
another probability for the numbers. So
Right.
it won't be like 52, like 62, 1 to 62, like it will be like, 1 to 52 plus, 1 to 10.
For
And it will
example,
be the same.
no. But if you, okay, the idea behind the numbers is that you represent each number by byte. Byte has 8 bits in it, right?
Okay,
So you want to represent all the numbers and all of the letters by the same byte.
so as
So the question is, what is the smallest number available?
so when you're talking
for
about a
bytes.
system, you're talking about 8 bytes.
Yeah, all the possibilities. Yes, exactly. So for example, the letter A will be 0, 0, 0, 0, 0.
Yeah, that one I got. I just don't fully understand what is the meaning of a system and the different, probabilities inside a system.
So let's see in a minute 2 examples, and maybe it will be more clear. And I think that you will do a nice example with Izal. He has it in his presentation. So he shows why this is the number. So you calculate together all the possible representation, for example, of a fair coin,
Okay,
of 2 toes of fair coin. This we can do it also here. Yes.
I just didn't get why from 62 we get 8 bits.
So when you put, I don't fully remember the calculation, so I'd rather do an example that I fully remember, okay? So first of all, the units of entropy are bits, okay? So when you calculate it, you don't have any more probabilities. And sometimes when you use it ln instead of log, sometimes it is common in the literature. So this is called nuts instead of bits. Bits come from by ts, right? 2. Okay, so it's by something 2 is. This is what bits means. 2 is.
When we do 2 to the power of 8, we obtain 200 something, while when we do 2 to the power of 6, we have 64. Plus
2 to the power of 6, yes.
64, so it
Yes.
means that we just need 6 bits actually to cover all the letters and numbers, no?
Maybe, but maybe we also need all 3 sides. Is there some,
Ah, okay.
right?
But if we just stick to letter and
Yeah.
number, it means
So
that
you are
this
right.
6 would be enough.
So 6
And
times,
and if we do 62 times
no, so
stuff, we obtain
So it's not it's not
Right.
62, so let's say this 64, so it's we have 64 times 1/64. Yeah, you are right, it is 6.
yeah, I told
Yeah.
that with 62.
Yeah,
it's
you are
like
right.
5.9.
Exactly, yes.
Okay.
So since you have 64 events with the same probability, so it's 64 doubled by 1/64. And then it's log 2 of 1/64, which is -6, as you say, doubled by minus, which is +6. You are right. This is the right way to calculate for a uniform distribution
Yeah.
only.
Yeah, but it's
Yes.
just to understand the meaning of
Yes.
entropy. Like it gives the number of bits.
Yes.
Yeah.
Exactly. So it says that 6 are the minimal possible for for all the ABC and numbers. Yes, for example. Do you want, okay, so let's have an example. Oh, okay, so let's see what is the entropy of the paradigms.
Could we just see how the calculation is?
Yes, I will show you in a minute. Just let's start with easier examples, okay? So a paradigm might have the output of 1, 2, 3, 4, 5, and 6. And let's say that I play a game, then I throw a die, and then I want to tell Avia what was the number of the output of the die? What was the outcome of me rolling a fair die? And I want to do it as sufficient as possible. So I want to use bits. So what will be the size of a bit that I will need to do it? So the probability of each one of them is 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6, right? So the entropy of a fair die, it's fair dice or fair die? I don't know.
So that will
Both. Is minus from n equals 1 to 6. So it's the probability is 1/6 times log of 2 of 1/6. Okay. And since I have again and again the same number, so this one equals to 6 minus 6 times 1/6 times log of 2 of 1/6. Okay. And does someone has a calculator that can tell us what is log 2 of 1/6?
In what cases would you like to change the amount?
To learn.
It,
Look, the level of the numbers is relevant only for computers, but sometimes it's really like instead of using base of 2, you use other bases, and then you can change to none.
I only have the basic log. I don't have log 2.
Okay, so let's do it with Wolfram.
Log 1 is like isn't log one, log two of one is like.
So log 2 of 6,
Log two,
it's 2.6. Okay, so this one equals to, so here it's 6
2.6.
times 1/6, this is 1. And then you have this minus, you can put it in, and it's log of 2 of 6, right?
Right.
And this one equals to 2.6. So if I have,
Wait, but doesn't need, it's minus, right? You put-
so the minus, I put it in, right? Because here it's also 6 by the
Okay,
minus.
Okay,
So minus over minus is 1.
yeah,
And then it's log 2 of 6, which is 2.6. Okay, so let's see, what does that mean? That means that when I want to send a VIA about the number that I got, I can decode it this way: 0, 0, 0 if I got 1. 0, 0, 1 if I got 2. 0, 1, 0 if I got 3. 0, 1, 1 if I got 4. And then 1, 0, 0 if I got 5. And 1, 0, 1 if I got 6.
Do we always round up?
What do you mean by round?
So that's-
Ah, yeah, because you don't have 0.6. But what does the 0.6 represent? That I had here another possibilities that I didn't use. The 1,
For 7 or.
1, 0, 1, 1, 1. Is that it? Yeah.
So we could have a dice of 8.
Yeah.
Yes. If we'd have 8, exactly,
2 to the power of 3.
exactly.
But even if you get a smaller number like 2.2, you would round up.
Yes, because you need this extra space to represent the other possibilities.
wait, so you're suggesting that if the probabilities are normal distribution, that we just can take the log of 2 by the, because always if the probabilities are no distributed, then the first one will always cancel,
Yes.
and also the log of 1 will also always cancel.
Yes,
So just log 2 to the power of,
exactly. You got it right. Yes.
okay,
Yes. And this is for a uniform distribution, but for example, let's talk about how ChatGPT uses information. Because the main problem nowadays in NLP was a very big question. How do you represent each possible word, right? Here, when we have each possible letter, it means that there are some combinations that are irrelevant, right? And some of them are more probable than the others, and so on. So what is the most sufficient way to represent all the possible words in the world? So this is what ChatGPT does. So he has this calculation. So I don't know if you did us not talk about the possible representation of words?
Ben
Talked about it, right? So,
to back.
excuse me?
Word to back.
Yes, exactly. So did he talk about the possibilities? So one of them is just saying that you have a vector size of all possible words in the world. Let's say it's 10,000. And then each word is represented by where there is 1, right? And when you represent it like this, you can train the system on these vectors. But this is very insufficient, right? This costs a lot of time because you need each time to go through 10,000 indices, which some of them might be empty. Okay, so instead of doing it like there is 1 word for anyone like this, so instead you can also represent the world by these possible vectors. So let's say if you have 10,000 words, words, sorry. And this is even before you start training the network itself, you need to decide how you represent the data. Okay, this is a very main question in data science, how to represent the data that you are given with. So instead of vector of 10,000, you can say that, let's say that the probability of each word is equal. Okay, this is not true, but let's say it is like this. So the probability of each word is equal, therefore you need, if you have 10,000 word, then it would be log 2 of 10,000, and this equals to log 2 of 10,000, 13.3. So it's 13.3, so we can have a vector of 14, which is much more sufficient than 10,000, right? And then we can say the following, and some of the PhDs about NLP, which is natural language processing, are about how can you take this down. For example, you know that the word I is much more represented than the word encyclopedia, right? And the thing about information theory, and we will talk about it, is that when you have a uniform distribution, this is the highest possible number of bins. If you have less, then you can represent it by less, right? You can say, for example, if it's the lower probability, I will represent it by 0, 0, and then another, and then the rest. And if it's higher, I will represent it by 1, and then the rest. And this one is even more sufficient way to represent code. So some of the basic NLP studies are just about how to represent the words in the language. Okay? This is an outcome of the information theory. Okay, I think that about the last thing I will talk during the lecture itself, the recitation, I mean. So how do you, so here is an example of how do you calculate an entropy of a neuron. So this is an open question. So you can either represent it by all the possibilities like we've done here. So here it's 8. Or you can say, I only care about what is the number of spikes, right? So here you don't have any spikes. Here you have 1, here you have 2, and here you have 3. So these are just only 4 possibilities, right? And then you can say that another way to calculate it is by counting the possible orders of each one. So let's say that the neuron responds to only when it's no spike, 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 and it does not represent to these 2. And then the question is, what is the information between the 2 neurons? And then even if you calculate it only for this part, we get something different. So the idea about how taking information theory into the brain regions is an open question. In the course, we will do it easily by giving you the probabilities, and then you will calculate the entropy, the mutual information, the conditional entropy, and so on. Some things that I will talk about in the recitation, and also Izhar will talk about. But again, I want you to go from here about this idea of representing by bytes and how to do it sufficiently. Okay? Great. Yes.
I have a question. So the quiz is tomorrow at 8, and I'm just because
The quiz?
Yeah, the quiz.
It's only 6 seconds.
The quiz that due on the 17th at 8 a.m.
I should have been at the 24. I think,
Okay.
and talk to Izhar, and as far as we've been talking about, it will be by discrimination. Okay, so until discrimination, the last thing that you, and also the coding.
The quiz from the recitation quiz.
Yeah.
No, so the thing is,
Okay, yeah.
we only talked about entropy, I think, now.
Oh, I wrote it for tomorrow?
Yeah, it's due
And
tomorrow.
now it's for next week, sorry. It's for the 24, and I will give you more time because if it will be the same day of his quiz. so-
But the other quizzes weren't discriminating.
We have a, when's the next
Sophie,
quiz?
send Ivar a
27,
question
24?
because as far as I remember, he wrote me that you're going to have another quiz
On the 24th?
on the 24 with the same subject, but maybe a computational one.
Same subject, same subject, and.
And also discrimination and decoding.
But we had so much.
But-
We can.
No, now it's really hard to get back.
What about the project? We don't need to do it?
The project is at the 1st of July.
No, it doesn't help us if it's on the 1st of July, we didn't learn it yet.
So I think you
It
should,
doesn't help, like, I tried to start it, like, last week and
Yeah.
it didn't learn anything.
so if you will need some more, I will give you another extra week. Don't worry, because now we really covered most of the course. So I don't care about giving you to the 8th of July if you need. This is 2 weeks from now, the 1st of July.
Yes, but we didn't learn the things. in-
We are going to learn it in the next recitation. And
Yes,
if-
on Wednesday, and then it's not gonna be 2 weeks.
Yeah, and if you need more, I will give you more.
Yes, but then you say we have also a quiz of Izar, and when we're,
Talk to Izar and be on it because I remember that he said that it's going to be at the 24th of June.
What? The quiz, right?
The second quiz, yes. This is what I remember. But I feel this is about the same subjects plus the last 2 subjects that we didn't have time to speak about, and I can talk with him maybe about the coding, if the coding will be in the quiz or not. Okay?
I mean, do you think it's necessary? I sent an email tonight because we see him tomorrow morning and I got
Yeah.
asked him to, you know.
I know that he wants to go on because we are really stuck now. I mean, like, I couldn't teach you the decoding because we were really busy with the analytical quiz, right? And then if we have another week like this, then we will just be stuck for 3 weeks during a shorter semester. So I don't know, if he wants to go on, he needs to be really clear about that. But on the recitation, I'm going to finish the coding. And I really believe that we can also finish information theory. And if needed on Sunday, you will have another reinforcement that I will have another 20 minutes about information theory if needed. Yes.
So, could you give us more information on how the computational quiz looks like what the.
doesn't
matter, format is?
I don't know.
Something else.
Uh,
So,
So it's like the easiest questions of the project. So you have, for example, a question about, it's like half of the questions in the project.
But is it also just 1.5 hours?
I don't know, and I don't know if it's how we do it. So you need to ask him. I don't know anything about
You
this.
need to
field.
write the code.
Yes,
in
without
Outlook.
internet,
No.
with no ChatGPT, yes.
No cheat. How does he know? Like, he cannot check with the people at home and.
So with the people at home now, but
Yeah.
here you have to be with your laptops and he goes through to see that you didn't use the internet and you need to,
Memorize it.
What is
and you need to take off into airplane mode or something like that.
but you know, even if someone is. coding-
But this is not the right question to ask either me or Izar, because
Okay.
then he will look for it. Okay,
Look for what?
for who is opening the